me just introduce you. Our next speaker is Anatoli Juditsky from the University of Grenoble in the Alpes, and he's going to talk about large-scale optimization for statistics and learning. So, welcome. Thank you.
Thank you very much. So, basically, I will speak about just one problem, and which is motivated in part by classification problem. So, what the simplest problem of classification is the problem of linear discrimination when you have two sets of points. And basically, you want to find a hyperplane which separates two sets. And so the attributes to the points, the features, so these are the coordinates in the space of these points, and you have the labels which are plus minus 1, which you can say black points and white points, so you want to find this separator. So, and basically what you want to find, in this picture, of course, the two sets of points can be nicely separated, but in this situation they cannot be separated by hyperplane. What you want to find is the hyperplane which minimizes what they call the empirical risk of classification, so that means the number of wrongly classified points. Okay. Unfortunately, this is not a good optimization problem because this empirical risk, of course, it's not a convex function. So you transform it. So you try to find the convex proxy which will be efficiently treated, which can be efficiently treated. So let us come to the problem of spot vector machine SVM classification, which is very simple. But basically, okay, this is some sort of simplified form. I have removed the constant term, the shift. So this will be the separator. So the W, this is the vector of the separation, and the classifier will be the sign of W transpose X. So it will be plus or minus 1. Okay, they call it linear classifier. Okay, where X are the points in the space and Y are the labels, and basically you want to fit the classifier, and there is a fitting problem. So you have to you have a part of the criterion you want to optimize to find your classifier W will depend on fitting the data, so correctly classifying the points, and then you have to penalize to avoid overfitting. And for instance, in this problem, I'm sorry, I'm speaking about trivial things, but okay. You can classify with the norm, L2 norm of the classifier. You can penalize with the L2 norm of the classifier, and as it happens, it corresponds to maximizing the margin of the classification, meaning that if the two sets are nicely separated, can be properly separated, that the classifier which you will obtain by minimizing the L2 norm of W will correspond to the maximum thickness of this band. Okay, so this the loss which is used, which should be convex to be efficiently treated, basically it corresponds to sort of convexification of the empirical risk, and this is non-smooth loss, which is actually so. So you want to approximate the function, which is step function, and basically this is not convex function. So in a sense, the best convex approximation will be piecewise linear function. This is exactly this what they call hinge loss, and you can smooth it using the logistic loss, which will be the smooth approximation of this, in the sense of this piecewise linear loss. So you minimize the stuff like this. If you correctly choose the penalizing coefficient by cross-validation and so on, you will obtain say, a good classifier. Okay, so you can extend this multi-class classification. So basically what you can do, the primal thing you can do, you can just to use one versus the rest classifier, or you can do something smarter. Okay, by introducing the matrix of classification, the classification matrix W, so now the classifier will be the matrix, the answer of the classifier will be, so you compute the scalar product, you compute the product of the matrix with your X, and to find the answer of the classifier, you take the maximal component. Okay, so the number, the index of the maximal component of this vector which you will obtain, it will be just the class at which points your classifier. And to train the classifier, basically you can use penalized things like this. So you can use multinomial hinge laws, or you can use multinomial logistic laws, which basically it's a direct extension of the previous one. When you look at the answer of the classifier and you compare it to the true answer. Okay, and you want that true answer to be the maximum of all the answers. So, and this loss, okay, this basically this is the upper bound of number of wrong answers. So now the question is how to choose the penalty. Okay, so what people preconize in machine learning, they like this type of penalty, which what they call nuclear norm, which is just the sum of singular values of the matrix W. Okay, there are many other choices. For instance, if you use one versus the rest classified, this will be just L2 norm. Okay, but this norm has several advantages, and people like it because, okay, if in a sense you have a lot of features, but your classification depends on certain linear combinations of the features, okay, that in fact living in very high dimensional space amounts to living in small dimensional subspace in reality of the space. So it may be very useful if we knew the subspace where significant features live, then of course our classifier would be much simpler. Okay, so this is really related to reduced rank classifiers and reduced rank regression. So what we would like, imagine that we know that there is some small dimensional subspace which is important for us, but we don't know which is, it exists, but we don't know where is it. So what we could try to use is to minimize the rank of our classifier, which is again, it's non-convex problem. And this minimizing this sum of singular values of the matrix, it's in a sense, it's the best convex proxy of this non-convex optimization problem. Okay, so it's in a sense like L1 minimization, like class, when you penalize with L1 norm of the vector. Here you penalize with this nuclear norm of the matrix, which is L1 norm of singular values. Okay, so you expect that your singular spectrum of this classifier will be sparse. Otherwise, the classifier will be of small rank. Another story, another famous story, which also leads to this kind of, which can lead to the same kind of problems, is this Netflix story that, okay, I believe that everybody knows what is Netflix, and I don't use Netflix personally, but I don't know. I think that many people, especially people with kids, they know what is Netflix. Okay, so this is a huge database where you can choose your movie, and what makes success of this one with respect to maybe some other ones from the very beginning, that they had movie recommendation agents. So this is just an example of recommender systems, and this is not mine. This is a friend of mine, and actually it's not even his kids. Okay, the page of Netflix, and it proposes you some movies to see, and what happened actually in 2008, Netflix proposed they made public a database. Okay, of 18,000 titles and 500,000 users, and they put the price. Okay, they put the price about this, and they offered $1 million for the first team, which, so they had their mechanism of recommendation and prediction of the scores of the, what user would like to choose. And for 10% improvement, they offered the price for 1 million and 50,000 for improvement by 1%. I think that this is a famous story, and actually it took 2 weeks to pass 1% mark and 3 years to reach 10%. And actually, this is a nice example, I believe, of, okay, the price itself with respect to the resources engaged in solving the problem was, of course, negligible. But that was a nice example of what now goes on in learning community and computer science and statistical community, this new paradigm of working. And actually, so people wanted to solve the problem, and there were a large number of teams working on the same. They exchanged the result, and actually each success was fast propagated, and other teams incorporated the new things, and actually in 3 years they solved the problem. And there was a big number of researchers working on this. So finally, the anecdote is the 2 teams arrived with, I don't know, a few minutes interval with the solution, and I believe that the first one got 1 million, the second one got nothing. Or finally, they gave some money to the second team too, whatever. In between, there were some problems because some people discovered that basically the Netflix data can be reverse engineering to understand what were the users inside. So they removed the first database, they put the second another database, which was privatized and so on. But that was another story. So why it's interesting for us, because so we did not participate in all this contest, we arrived too late. Okay, so this is, you can see, so this is the problem of collaborative prediction. So this, for recommender system from Netflix problem, you can see is like this. So you have the huge matrix, okay? You have customers, the customers of Netflix, you have the movies, and each customer attributes the score to a movie, and our objective is to predict each customer's score for each movie. Okay, so we want to complete this matrix, and basically you have a lot of customers, you have a lot of movies, and each customer rates, I don't know, a few movies. So this matrix is really sparse. Okay, and basically what you want is to recover, given this information, you can recover the complete matrix. Okay. And of course you cannot do this, okay, because it's very sparse. You cannot do it without imposing some very strong constraints on the matrix. And basically, the constraint you would like to impose would be in fact, that this matrix has a small rank. Look, for each user, the rating of each user for each movie, you can represent it just like a product. The one vector which represents, so for each user, you can say that, okay, you have the rate of movie I by the user G, it will be the scalar product of 2 vectors. One represents the user, and the second represents the movies. So then the big matrix X, the scores for all users, you can represent it by this product of 2 matrices. Okay? And basically, you can think that these matrices are of small rank. Why? Because typically there are a few types of users. Okay? So users which like, I don't know, James Bond movies, they maybe would like less Fellini movies. I don't know. Something like this, and there are kids, and there are adults, and there are whatever. So there are a few types of movies, there are a few types of users. So basically, this matrix may be of low rank. Okay? And if the matrix is of low rank, then the number of intrinsic variables is small. Much less than the total number of entries in the matrix. Okay, so what we could try to do is just to fit the matrix X. So A are our observations, the observed entries. Okay, so you have the loss. Okay, so your matrix should be close to the observed, and the observed entries of your matrix should be close to the entries you see, and you penalize with the rank of the matrix. So, of course, this problem is non-convex and difficult, and actually what you can use is the proxy of this problem, which will be substituting the rank with nuclear norm. Okay, so we come in a sense to the same type of the problem we had before. Okay, so what we need to solve this kind of problem where we have smooth function of a matrix plus a nuclear norm. So this is a nice problem which is basically in the, it's semi-definite programming problem here. And okay, if you have MATLAB on your computer, Python, you can use CVX to solve this kind of problems, okay, to high accuracy. But actually, typically what you will use is interior points algorithms, and actually these interior points algorithms, they're very nice, they're very advanced, very smart, but they're Newton-type algorithms, okay? So the complexity of iteration, so in few iterations, they will give you a very high precision solution to the problem. But the complexity of iteration will be the number of variables to the power 3, okay? And if you have a huge problem with a lot of variables, you can get a problem, okay? It can be difficult. So these type of algorithms, they work very nicely on economical problems with millions of variables. And the reason for this is that economical problems, that typically their matrices are very sparse, and they're sparse and structured. Otherwise, how could people enter this economical data in the computer? Okay? When you look at the problem in machine learning and signal processing, the matrices are dense, typically. And this is catastrophic. So already the problems, simple problems with like 10,000 variables can be too large for these solvers, for this type of techniques. And SDP problems, and we are in particular interested with SDP problems. So SDP optimization, just 10,000 variables or 100,000 variables, it will be too much. And 10,000 variables is just a matrix 100 by 100, okay? So this is ridiculous. So we need some other methods, and basically, strangely enough, what happens, we have to do a step backward. Okay, so instead of using very advanced technique, we will use all the techniques, which will be first order method. And these methods much better fit large dimensional problems. So if you look what happens with the SVM, so typically they beat the SVM, they work very nicely. They work very nicely for the SVM. Okay, so what is the feature of these methods? These are the methods with very simple iteration. Instead of Newton iteration, which is complicated, these are just like gradient iterations, okay? And the new results about these methods say that actually the number of iterations of this method to attain some accuracy do not depend actually on problem dimension, okay? Not good news about this is that convergence is slow. Okay, it's sublinear, unlike this interior point method. So what are these first the methods? If you want to solve the same problem where I was talking yesterday, so minimize the convex function, convex continuous function on a set. Okay, for the simplicity, we will assume that the function is differentiable, so you can use the gradient descent algorithm. Okay, the gradient descent algorithm, you just make a small step in the direction of the anti-gradient, and then you project your step on the convex set. And what you can show that in terms of optimality of the trajectory of the search point you get, you have this bound. So you see that the error in terms of your function decreases like 1 over k. Instead of epsilon to the power minus k, as it would be for interior point methods. Okay, so the convergence is fast, but in statistical problems, we don't need high accuracy. Okay? And this is very nice. Okay? And then when people, so there was big research in 80s and 70s on first order methods, but they remained like unused, the result they had. So for instance, the Nesterov result of 84 about the optimal, actually the gradient descent is not optimal for the smooth optimization. And the optimal algorithm has a rate 1 over k squared. So in 84, Yuri Nesterov developed the optimal algorithm, and it was unused till the beginning of 2000. And then now it's you type Nesterov optimal accelerated gradient algorithm, you will get I don't know 10,000 of hits. So okay, you can generalize it for non-smooth optimization. There are many advanced methods, Actually, I was talking about constraint optimization when you have a bounded set, but you can change it, you can extend it for penalized, unbounded problem, and so on. Okay, and the good things about this method that the rate of conversion do not depend on the problem dimension. Of course, each iteration, the computation you will have to do will depend on problem dimension, but the number of iterations to attain the accuracy, the necessary accuracy, will not depend on the dimension. Okay? And in the situation then when we don't need high accuracy, this is very good. So all we need to implement this type of the methods, we have to be able to efficiently compute the gradient, okay? Meaning that we will have to implement the first order oracle. And we want to do correctly, efficiently the projection. Unfortunately, both of these things become problematic if we, once again, we pass to big dimensions. Okay? And if we take the example of imaginary data set, the dimensions of this data set they are huge. So you have a lot of images, you have a lot of features. This is a huge dimensional data set. And this standard first order method become very difficult to use. So there are basically two works to compute the oracle, to compute the gradients, subgradients, whatever. You have to do matrix vector multiplication, but even these operations, which seems to be very simple in algebra, they become very expensive. And you have to compute the projection. Okay? I will not talk, of course, I have no time to talk about the first one, I will just talk about the second one. And, okay, I will talk about the second part. So once again, we have to make the step backward from this gradient algorithm, this first order algorithm, and we have to come to the algorithm. We do not use the projection. Okay, what is the problem with projection in our problem? What does it mean to project in our problem? So our set on which we want to project, it's the ball of the unit, the ball of the unit nuclear norm. Okay, so this is the ball of in the matrix space of matrices such that the sum of singular values is bounded by 1. Okay? And all methods to project on such ball, what we know, amount to compute the singular value decomposition of the matrix. Okay, so you have to compute singular values, singular spectrum of the matrix. Okay, and this is, of course, will be very expensive. Now, there is an old algorithm, which is probably the first known algorithm of constraint convex optimization, which is due to Margaret Frank and Philip Wolff, which was developed in 1956, and which is simply even then the gradient descent. Okay, so this is a method of smooth convex optimization, so where you want to minimize the function on the convex set, and what you need to do to implement this algorithm, you don't need to know how to project, but you need to know how to minimize the linear function on your convex set, which is simpler than projection on the set. Projection on the set is a quadratic problem, okay? And minimizing the linear function on the set is just a linear problem on the set. So, look, when we want to minimize the linear function, what is the linear function of the matrix? It's just the trace of, so there we have matrix Z, and we want to compute the scalar product, minimize the scalar product of Z and X on the set of nuclear norm bounded, on the ball of nuclear norm bounded by 1. Okay? It means just to minimize this trace. Okay? And the ball of the nuclear norm bounded by 1, it just, this amount, so, okay, this is the linear function, minimize the linear function on the convex set, it means that the minimum will be attained in an extreme point, and extreme points of this set, these are just one-rank matrices U, V transpose, such that the L2 norm of matrices, the Euclidean norm of these vectors, are bounded by 1. So you have to minimize just this trace, which means this will be minus maximum of E transpose Z times U, okay? And this is just, you have to compute the principal singular value, okay? And the maximizers will be corresponding singular vectors. Okay, and this operation may be much easier than computing the complete singular value decomposition. Okay, for instance, you can use the simple power method. Okay, most often, which will be much faster. Okay, than just computing the whole singular value decomposition. Here you see, depending on the size of the matrix, this is 3.1, this is 3.5. So these are the matrices between 1,000 and I think the size 1,000 by 1,000 and 16,000 by 16,000. You see that the ratio becomes like 300 already, and it grows even faster when you have big matrices. This is the ratio of time needed to spend just the principal singular vectors and the whole singular vector, the singular value decomposition. Okay? Now, how does this Frank-and-Wolf algorithm works? So this Frank-and-Wolf algorithm, what does he do? So imagine that your current search point is x. Okay? You have the gradient of f at this point, and what you have to do, so you compose using this gradient, you compose the local linear approximation of your function. And instead of doing like going in the direction of the gradient and then making the projection, what you do, you just minimize this linear function on your set, and you take this point, the minimizer on the set, okay, of this linear function, and you go in the direction of this point. Okay, so instead of doing the gradient step and then projection, you just minimize this linear function and go and do a small step in the direction of this minimizer. And basically, surprisingly, the rate of convergence of the algorithm, the rate of convergence of this algorithm is 1 over k, so it's like the gradient descent. Okay, but what you need is just to, so if we implement this strategy for a nuclear norm minimization of the ball in the nuclear norm, you will need to compute the direction in which you have to go. You just need to compute the pair of two singular vectors, the principal singular vectors, corresponding to the direction in which you want to go. Okay, and it works pretty fine, and especially in matrix completion problem. This collaborative filtering problem, like Netflix problem, it works very nicely because matrices are very sparse. So to compute the singular vectors, principal singular vectors, it's very easy because you multiply very sparse matrices with vectors, okay? And it can be done very fast and without big trouble. And you can treat huge matrices just without any problem on normal computer. Okay, so just matrices like, I didn't go to the size millions by millions, but if I had a little bit more memory, okay, I could do this. So just on a normal laptop, you can treat matrices like of size 500,000 by 500,000. Of course, they should be very sparse. Okay, these are random matrices, but it works pretty nice. So you have very nice convergence rates. And just computing to the relative accuracy 1%, solving this optimization problem, it takes less time than just computing one singular value decomposition of the matrix 16,000 by 16,000. Okay, you can also do this, of course, for a problem of multiclass classification. So we had the data, we have extracted the data. So this all was done in MATLAB, okay? So we have done everything by hand, so you can extract the data from ImageNet dataset. And actually, there is a part of the dataset which called vehicles. And okay, there is some machinery. There are our friends from computer science and image recognition. They know very well this machinery, so they helped us to extract descriptors and so on. So, and then we just launched our optimization algorithm of this out of this problem to obtain. I don't know if you see anything. These are two principal eigenvectors of the classifier we get. So this is the result, okay, after 1 hour of computation. Okay, so thank you very much.